אני חושב שזה נובע מההחלטה של הרזולוציה שלנו, אתה יכול לשנות את הרזולוציה פה? לא, כי עשינו מירו. אז בואו נשנה בחזרה למצב הקודם ונזיז את זה לדיספלי השני.
אוקיי.
אז חזרה לדיספלי. ובואו ננסה use as.
כן, זה בדיוק. זה.
ואז...
את המצגת תגרור לכאן פשוט.
את המצגת תגרור לכאן?
לכאן, כן.
באיזה כיוון?
אני חושבת שזה לכאן.
הנה פה, יפה. בואו נראה אם עכשיו זה יותר טוב. נראה שכן.
פשוט עושה קליק קליק.
רגע, אבל עושה פול סקרין.
כן.
אני חושבת שזה קומנדוס.
אוקיי, הצלח. זה המיקרופון?
אבל זה לא קשור אליך.
המיקרופון, זה נכנס לכיס, זה תסע. התאורה בסדר?
אני חושב שכן.
אז אני...
Okay.
Let us start. So I welcome you to the 11th lecture series in honor of Professor Dvoretzky. Dvoretzky is the Vice Laureate, was a prominent mathematician specializing in functional analysis and probability with classical theorems concerning normed spaces and probability distributions. Among his positions and roles, he was founder of the Israeli Institute of Advanced Studies and of the Israeli Academy of Science. He was president of the Aizenman Institute, chief scientist of the Ministry of Security, member of the Atomic Energy Committee, and won many prizes and honors. I should also say that he wrote in the early 50s the best probability one textbook, in my opinion, to date. Professor Michael Aizenman will give today's talk. He's a Thomas D. Jones Professor of Mathematics, of Mathematical Physics at Princeton University, among the cornerstones of today's mathematical physics, with contributions to almost all of its aspects, including quantum field theory, classical and quantum mechanics, percolations theory, spectral theory of random operators, and many more. He's been awarded many awards and honors, among them the Nobel Winner Prize, the Breuer Medal of the Dutch Mathematical Society, and the Henry Poincaré Prize. For many years, Professor Aizenman has also been a banner bearer for the philosophy that deep mathematics must also be comprehensible. And hence, I'm truly looking forward to hearing his two independent talks today and on Thursday. And now for today's talk, titled Rumination on Matrix Convexity and the Strong Additivity of Quantum Mechanics. Michael Aizenman, please.
Does the mic work? Yeah. Well, thank you very much. It's a deep pleasure for me to be here. I am an alumnus of Boger of the Hebrew University, and I'm getting emotional each time I get to visit it. So excuse me for that. It's also a pleasure to see the dynamics of developments around the campus changes from each visit, from one visit to the next one. It's also a deep honor to give the Aryeh Dvoretzky lectures. In fact, I did not intend to mention it now, but perhaps in the next one. But the theme of the next talk would be viral nature of ideas in mathematics, in science. Ideas pop up in one field and then they inspire by analogy similar concepts in another field, and like viruses, which like the development of viruses, actually when the host is changed, that often strengthens the viral idea. I'm mentioning it now because something like this has happened in my work vis-a-vis contributions of Dvoretzky. Among the results which Dvoretzky has established is the theorem by Dvoretzky, Erdos, and Kakutani about Brownian motions, the intersections of Brownian paths. So Brownian motion is a random walk, kind of scaling limit of a random walk. It's parameterized by time, which is one variable. But if you're asking for the intersection properties of the tails left by the Brownian motion, well, in 2 dimensions, they obviously would intersect with positive probability. It's hard to avoid each other. But also in 3 dimensions, intersections occur. And they stop to intersect only in 4 dimensions and higher. The intuitive explanation for that is that the trajectory of the trail of the Brownian path is 2-dimensional, even though it's parameterized by 1 parameter. And so the content of some of the works on this were done jointly by Dvoretzky, Erdos, and Kakutani. This is not a place to teach you about Brownian motions because there is such deep expertise in the audience. However, this theorem actually was in my mind when I was working years later on the scaling limit of critical Ising model and on related issues which were of relevance for quantum field theory. In Ising system, this is not the subject of the main discussion, so I will not define it, but for those who know it, it's a system of binary classical degrees associated with sites on the graph, which may be the d-dimensional ZD. The nature of the spin-spin correlation, sigma 1 up to sigma n to n, that's given by a sum over a kind of an extended system of terms which can be associated with loops, except for lines which lead a prescribed set of sources, which are these sites, properly normalized. When you extract the backbone of this representation, you end up with spin-spin correlation sigma x, sigma y, being given by sum over paths from x to y, paths which are parameterized by time, of a certain weight, rho gamma. The weight is not as simple as the simple random walk, but it shares certain properties. And this theorem kind of opened my eyes to the fact that these paths like that, even though they are much more complicated, do not have such elementary representation as you have for Brownian motion. Potential theory is still underdeveloped for that. They may also share the intersection properties that are described by that. Non-intersection of paths in high dimension translates to the fact that the correlation, the expected value of product of a finite number of such variables is given by essentially sum over pairings of product of 2-point functions. When you look at this, you realize that this is a Gaussian structure, and that led to the news that scaling limits of critical Ising models in high dimension, high being d greater or equal, at that point, the initial proof was d greater than 4 with kind of weak equality sign, would be Gaussian. Translation of that to quantum field theory, to constructive quantum field theory, was that in 4 and higher dimensions, we would have difficulties producing non-Gaussian field theory, which was the objective of this constructive project. So it was kind of a leap of insights from Dvoretzky, Erdos, Kakutani to Ising model 2, phi for field theory. This project was completed to d equal 4 in a joint work with Hugo Duminil-Copin fairly recently. And the latest progress on the subject, which also kind of brings us back to the beginning of this, is something which I heard just last week in Geneva. There are results currently proving that this limiting theory is not only Gaussian, but is also the free Gaussian field, the Gaussian free field in high dimensions. Namely, these rescaled weights actually have the distribution of Brownian paths, like in the theorem that started this chain of insights. So this is a digression, but I could not resist it. let me now come to the main topic of the presentation. The subject is ruminations on matrix convexity. I would like to talk about this concept a bit, and strong subadditivity of quantum entropy. These are two separate lines of investigation, two separate topics, and I would like to present, I would first present the story of the matrix convexity and then show applications of that. So let me just read the abstract because it summarizes these two tracks. So it may be a fair guess that people heard about Loevner SLE, the stochastic or Schramm-Loevner evolution. And the name of Loevner is nowadays very familiar to certainly probabilists and beyond these mathematicians. There's this marvelous tool which Loevner introduced, and Odette Schramm turned into a potent tool in studies of conformal limits of critical stat-mech problems. What many people do not know is actually that Carl Loevner also made another contribution. Of course, you may well know it because there is a massive book on the subject by Barry Simon, and he's well familiar here. So many of us did not know about that. So I would like to introduce the other Loevner theorem and explain its relevance for the subject. Then I would use whatever would be said here to provide a more elementary derivation of the Lie-Braskai theorem on the strong subadditivity of quantum entropy. The extension of entropy to quantum systems goes back to, well, the version that will be discussed here was introduced by John von Neumann. Formally, it looks as similar to the classical expressions of entropy, which is integral of rho log rho minus sign. Instead of integrating, take the trace. But while the classical analog provides a guide to what properties may the quantum object have, the proofs typically are very different, and there are some surprises along the way. So a property which I would introduce more explicitly, which is the strong subadditivity of quantum entropy, was mentioned, this was established by Lieb and Raskai in 1973, some 50 years ago. 2 years ago, Elliot Lieb received the high prize of American Physical Society for his contributions to the field. The proof of this result was particularly selected as a notable contribution. The proof was rather non-trivial, and one reason I'm presenting these two topics is that I wanted to show how can you establish this through a sequence of rather elementary steps. So these are the two subjects of the presentation. So let me turn to the first. So if we know what's monotonicity, is this blackboard visible? I mean, I can see it, but from experience I know that sometimes you cannot see. Is this, sorry? There is a light. I see. So, okay, I will not be using it very heavily, so let's not do that. But you know what a monotone function is. Oh, that's great. Is the screen still visible? Perfect. Okay. So take a function f, which takes is defined over the reals, takes real values. You know the property of monotonicity. There's a natural way to extend it to function over matrices, n by n matrices. Well, you have to stop for a moment and think what is the function f when applied to a matrix. But the spectral calculus answers how to do that. So one way to do that is, of course, you diagonalize the matrix. If M is equal to a unitary transformation of a diagonal, f of M is the transformation by the same unitary of f of d. This works perfectly well for polynomials, and it's a natural definition for functions of a matrix. A function f is said to be matrix monotone if its extension to n by n matrix, if for every n, its extension to n by n matrices is monotone as a quadratic form. So over the matrices you introduce, or operators, you introduce a partial order where you say M2, there's a typo, it should be M1. M2 is greater than M1 if and only if expectation value, diagonal elements, expectation values in any vector of M2 dominate those of M1. Natural notion of domination, if you wish, if the difference M2 minus M1 is a positive matrix. That's partial order. Once you have partial order, it makes sense to talk about monotonicity. Monotonicity means if M1 is greater than 2, would f of M1 be greater than f of M2? And there is a trivial class of monotone functions which are just linear. F of M is A identity plus B M. If A is real, B is positive, that would be trivially monotone. And then comes the theorem of Loevner, which is quite striking, that among the measurable functions on R, these are the only cases of functions which are matrix monotone to all orders. I must confess that I was not aware of this until not that many years ago.
What does it mean to all orders? To all sizes?
Sorry? Oh, for all n.
Orders of the size.
All of the dimension, for all dimensions. So, to all order, it means for all n. These are matrices which are n by n. If you functions f which have this monotonicity, regardless of the dimension of the matrix, actually you have only the trivial examples. Well, but then however, the next observation, it's not observation, but the theorem of Loevner, the extension of this is that you get more examples if you restrict to matrices of prescribed of spectrum contained in an interval. Or in general, if you specify let's talk about intervals. If the spectrum is restricted to an interval AB, the class of matrix monotone functions, in addition to the trivial linear case, includes also functions which look like the resolvent of essentially functions which look for which f of m is 1 over m minus u times the identity. In that case, the monotonicity for such functions, the monotonicity is not hard to prove, and then by the observation that monotonicity is preserved under convex combination, you get the Loevner's characterization of matrix monotone functions essentially as the kind of spectral representation that you are familiar with from the theory of Herglotz functions. In other words, matrix monotone functions, the functions which are listed here, take the upper half plane to itself, they have the Herglotz property, and they can be represented by linear combinations with suitable positivity condition of U. So now Loevner's analysis focused on the study of dividend differences, which are essentially the divided difference is the analog of the slope of a chord, which is the difference between the values of the matrix for between two matrices divided by with the.
Sorry.
Yes.
How does the square root function fit into the picture? Because it is matrix.
Square root would be matrix concave. Yes. Yes, it would.
Matrix monotone?
Sorry?
It's not matrix monotone?
Oh, no, yes, it is matrix monotone.
So
Yes.
how does it fit into locus?
Square root function is a Herglotz function. It takes, so now that square root function can be written as a linear superposition, as an integral, in fact. The square root can be written as an integral of, can be written as an integral from 0 to infinity of du over suitable u minus x minus u, and I have to put the right power here to make it convergent. To get square root, I think that I have to multiply probably by square root of u. No, sorry. Or divide, perhaps divide by square root of u. Do I have it right?
Because your matrices are self-additive. matrix of a negative definite, you won't have square roots.
Right, but no, but for matrices, if you look at matrices whose spectrum is support, we are talking about. It's a good question. If you restrict to matrices whose spectrum is positive, non-negative, on such matrices it makes sense to define m to the 1/2. And let's see, I think that I may have my u's crossed. It should be du over, I think, u to the 1/2. Let's see, I think the dimensions of this, I think up to constant, that's true, and the constant is positive. So, but that's a good example. We have a function which can be represented as a linear combination. U is a real parameter. It's a linear combination with positive weights of functions precisely of this type. Rather than do the calculus, another way to check that is to check that square root, the imaginary part of z to the 1/2, when z is in the upper half plane, when you take the right branch of it, is also non-negative. So imaginary part of x plus I1 y to the 1/2, take the principal value of that is positive for y. That's you can easily see it for the square root function because square root just halves the angle. And under this criterion, the Herglotz representation would give you essentially this representation of the given function as an integral of these simple functions. So you get an interesting class of such functions. Now, nowadays, let's see. Trivial comment. The condition of matrix monotonicity to all orders, in the sense all n, is essentially equivalent to operator monotonicity extended, the notion being extended to operators on Hilbert spaces, separable Hilbert spaces. Now, Loebner had a student, Krauss, whose name is also not, quite familiar these days because of contributions to what led to quantum information theory, among others. So Krauss turned his attention to matrix convex function. Convexity is closely related with monotonicity because it just says that the chords are monotone. So you would not be surprised that this result has an extension. So let's see, here is a formal definition. A subset, first of all, a convex set is a subset of an affine space which has the property that the convex set is one where for every pair of points there is a chord. The chord linking them is also included in the set. That's a convex set. And a function is convex over this set D if it has the property, real valued function, if it has the property that for any such chord, the values of the graph of the function lies below the linear interpolation. So these are convex functions. That's a generalization of the natural notion of convexity. And related to Loebner's representation is the theorem by Krauss, which was completed by Bendat and Sherman, that the class of C infinity AB, infinity is not differentiability but degree of convexity. So functions which are convex which when taken to n by n matrix produce convex functions which are convex over matrices of prescribed spectrum in AB consists of functions which are presentable by such integrals, which are very similar to they are the natural extension of what we saw in answer to the question. So there's a rich discussion of the subject in a book, very thick, by Barry Simon, Loebner's theorem on monotone matrix functions. Also, there is an article by Efros, a matrix convexity approach to some celebrated quantum inequalities. That's kind of a precursor of this talk in Proceedings of National Academy of Sciences. The book, Simon's book is some between about 500 page long, and towards the end of it appears what may have been presented as a simple proof of the subadditivity, strong subadditivity on entropy. It's hard to call it simple if you have to read 500 pages to get there. So I try to present an alternative which is simple. Yes?
When you said function is convex on matrices, you mean the same according to Horns, but it's when you apply it for matrices?
When you apply?
You said when a function from V to R is convex. Now it's a function from matrices to matrices.
Yeah, okay. I think that I have an idea of what you are asking. So first let me talk about functions which go from functions f of m, where m is an n by n matrix. So it takes, let's start with real valued functions over self-adjoint n by n matrices. Convexity of such functions is defined by a corresponding condition where the statement that f, that should be capital F. What it says is that f, let me make, this is probably not the question, but let me just make clear. You often would see in the discussion this sort of an interpolation, 1 minus lambda x naught plus lambda x1. If x naught is one point, x1 is another, the linear interpolation going from here to there is through functions which would be referred to as x of t, which are 1 minus, also x of lambda, 1 minus lambda x naught plus lambda x1. When lambda is equal to 0, that's x1. Lambda equal to 1, you are here, and x lambda just travels from here to there. Convexity of this function, this D represents space of matrices, n by n matrices. Convexity means that the graph, again, has this property that along such a chord, the graph of the function is dominated by the linear interpolation by the function's values at the endpoints.
When you say, okay, so maybe you said the function are convex over the self-adjoint and matrices. But in the previous slide, you said that when we apply a function to a matrix, we get back a matrix.
Correct. So here I extended the notion of, correct, right. So in general, thank you for the question. In general, we are now extending the original function. We started with a function on a real line. And using the prescription which I described, you are extending it into a function from the space of matrices of given dimension n, in general into matrices of some other dimension k. And just as you can extend monotonicity to this setup, using the same language, you extend it to the notion of convexity. You can do that because convexity is expressed by inequality between the value of the function at an interpolating point and it's the interpolation of the values. And in that case, so what we are now talking about is the situation where the argument is a matrix of n by n, and the value f, the range, is matrices k by k. Inequality is interpreted in the matrix sense. For some, okay. So thank you for the question, and I appreciate being interrupted, especially as I'm mixing various notations and subjects. So while convexity, the first time you encountered convexity, you probably heard about the second derivative test, and that's how we often test whether a real value function of a reals is convex. You just take second derivative. It's a local test. But it has a global manifestation, which is expressed in the Jensen inequality, which says that if you have a convex set, here it's restricted to real valued function, but similar statement applies to matrix-valued functions. Convexity implies that for any probability distribution on with compact support within D, the average of f of x, where x is now ranging over matrices, the average of f of x dominates, in the appropriate sense, the function at the midpoint, at the barycenter of that. That's a Jensen inequality. It's extremely useful. Denmark was so proud of that there was a time when stamps which passed through Danish post office were stamped. The message is a mail was stamped by stamps which had this inequality on it, Jensen inequality. And the Jensen inequality extends to this multidimensional setup. So the original studies by Krauss and others of convexity used Levner's technique of looking at the divided differences. It tells you that what was learned is that if you restrict the attention to matrices of order n, you get it satisfied for a tighter and tighter sets of functions as n increases. It's strictly the class is strictly monotone in n. And the derivations are not the simplest. A local test of convexity in terms of second derivative is possible, but its natural expression is in terms of Frechet derivatives, and you very quickly run into formulas which involve tensors, and positivity of such things are rather difficult to establish. And in addition, it's very tricky to differentiate a function f, where f of m is of the form of the unitary transformation which depends on m, then the diagonal, another unit. Well, I would come to this shortly. Let's see. So as a step to simplify the discussion, I wanted to point out that a sufficient condition for convexity of a matrix is actually there exists a simply stated test of convexity, which is of the form written here. Namely, if you have a function defined over a manifold, second derivatives are given by tensor, and positivity of the Hessian can be expressed in corresponding terms. But another simpler way to test it is, instead of taking the set of mixed derivatives, it suffices to prove, it's essentially equivalent, that for any direction of transverse travel through that point, the Gateau derivative, which is just the differential derivative in this direction, is non-negative. And what we are talking about is taking a function f at m plus say tq. M is the matrix, q is a non-negative matrix. So the function is of the sum m plus tq. T is a real parameter. And to prove the positivity of the Hessian, what you want to look at really is what you need to establish is the positivity of the matrix elements for every vector phi of the derivative of that. That's kind of summarized by this relation. So it's a simple argument to prove that if you manage to establish such positivity, you can deduce that f is convex if you prove this over a convex set. The problem is that computing those derivatives is rather tricky, because if you, differentiating f of m plus tq, essentially, if you go back to the definition, means that you have to diagonal f. What you're really differentiating is u, a t-dependent unitary of f of a diagonal which depends on t u t. So it's one thing to study the spectrum of the matrix which depends on a parameter. You can do that. But now what you require is positivity of this sandwiched by U, which itself varies with T. So it's rather complicated. In that case, I would be intimidated by that. There's one case where I will not be, and that is in case of resolvents. So matrices of this type, 1 over identity, I hope the notation is comfortable. Let A of T be some matrix A plus TQ. In fact, A for T can be any T dependence, say smooth differentiable dependence. The resolvent, which is 1 over A shifted by a constant, that quantity we know to differentiate easily. That's the one, that's not the only case, but that's one of the few cases. The other is polynomials we would easily be able to differentiate. That is also easy because of the resolvent identity. The difference between, there's some inconsistency in the denominators, but the main point is 1 over matrix plus 1 over A plus delta A, where A are matrices, the difference in this obeys this algebraic relation. And when you take the second derivative of R of T, you get this, R of T is the resolvent. The second derivative is given by the sandwich. Here is the resolvent. It's going to be decorated on both sides by Q, which is Q is the derivative of the matrix. And then positivity of such combinations, sandwich combinations, is actually easily established when it's correct. So the point which I'm making is that for matrices, for functions which are linear combinations of resolvents, for such functions, if you have the representation, it's easy to prove the convexity. You would be discouraged that this is far from all functions, but actually the good news is that by the theorem of Levner and Krauss extension to convexity, that's all there is. Namely, for the function to be convex, matrix convex, it has to be linear combination of such terms. So actually, the message is, if you want to prove convexity, try to find the Herglotz representation for that and check its positivity. So that's the first part of the story. And just to show the application of that, it's something which was not appreciated at the time. As I mentioned, Lieb-Raskai theorem is 1973. It turns out that a few years earlier, Anderson and Duffin, in a paper which has many interesting results, included the statement that the mapping from K tuples of strictly positive matrices, A1 up to K, this to that, which they refer to as the parallel sum, that mapping is jointly concave over K tuples. They actually proved it for the case K equal 2 by an algebraic proof. In this case, what I described before can be easily applied. You can also prove the convexity of that by differentiating. The differentiations, in this case, are doable. The derivatives are easily written down explicitly, and positivity can be easily checked. This result was missed in part because it was like a golden needle in a haystack. The paper has many, many results, and the abstract does not even mention this one. Now, in addition to it's called concavity of parallel sums. Would anybody know why is it called parallel sums? Exactly. The Ohm's law for conductance or resistance, I will have to stop and think, is exactly that. The parallel connection of resistors is given by that expression. So it's the inverses which add up and then invert. So in addition to this, to the intrinsic interest in that, I want to show how this can be used to establish the matrix, the desired result for entropy, strong subadditivity of entropy. So I'm now turning page and starting the other subject. So just some quick comments about quantum systems. So in quantum physics, systems configurations are associated with rays in a Hilbert space. Observables are expressed in self-adjoint operators. States correspond to expectation value functionals, which assign to each operator expectation value, which is linear, positive, and normalized. So the expectation value of identity is 1. And in finite dimensional Hilbert spaces, that essentially means that the expectation in the trace is the trace of A times rho, where rho is a self-adjoint trace 1 matrix. Now, for a composite system, the Hilbert space describing a composite system is just the tensor product of this space, of the system spaces. And I use the abbreviation where an observable which acts only on one of the components would be sometimes referred to as A2, although its more proper way to list is this kind of tensor product identity on everything else except A2 on the second component. Now, in this setup, the von Neumann entropy of a state function is, oh, shoot, there's another typo. There should be a minus sign here. It's a minus trace of low log rho, just as the familiar concept. Now, if you have a composite system with many components, the restriction of this expectation value functional to a subsystem is associated with a state operator which acts only on that component. So we refer to that in this case as S1 or S12 or S123, depending on the subsystem that you restrict to. And the corresponding entropies are denoted as here. Now, in classical systems, entropy of a probability distribution can be interpreted in different ways. One of them is how much information would be revealed by measuring the observable. From this perspective, it's very intuitive that the entropy is subadditive. In particular, we have this property that the entropy of a system which consists of two parts is less than the sum of entropies. Actually, let me step one more. Let me go one step back. What easily follows from this information theoretic picture of entropy is that the entropy of a subsystem is smaller than the entropy of a system. Of course, there's more information to be learned if you measure the total time system. Gee, this is false quantum mechanically. This simple relation that the entropy of a combined system dominates the entropy of its subsystems is not true.
What do you mean by a subsystem here?
I'm going back to the situation where if you represent the relevant, I would represent by degrees of freedom. For example, if it's a system, it can be expressed in different ways. If you have a system of spins, one subsystem, the subsystems may correspond to subsets of spins. Or else, if you have a quantity with many degrees of freedom, this would be different sets of degrees of freedom, like position, momenta, and so forth of particles. So the entropy of the whole classically is greater than the entropy of the subsystem. Quantum mechanically, it's not true. Any idea why? What would be a counterexample? Yeah, they do not commute, but there's a striking counterexample. Think of a situation in which over the full Hilbert space, you take a pure state. The density rho is a rank 1 operator. The state is in some state vector psi. It's kind of the most elementary quantum states. The density rho is, in Dirac notation, this rank 1 projection on a vector psi. Its entropy is 0. Classically, if the entropy of a classical system is 0, discrete system is 0, it's because the probability distribution is a delta function on some configuration. If you specify a configuration of a composite system, you have specified its restriction to A as well as to B. So if the entropy is 0, it's a pure state in each of the subsystems.
But
Quantum mechanically, that's not the case. Quantum mechanically, if you have and in fact, the reason is actually, I am happy to talk about this at the Einstein Institute of Mathematics because it's related to the fundamental challenging paper published by Einstein, Podolsky, and Rosen of Technion, in which they pointed out to the bizarre, initially striking properties of pure states, for example, like this one. That's the wave state of Einstein, Podolsky, and Rosen. Later, if challenged, I'll be very glad to spend some time explaining why is it so philosophically challenging in terms of foundations of quantum physics. But this topic was eventually further explored, and there is something called Bell states. Bell extracted from these inequalities which can be measured and which really established that you cannot present a quantum system as just partial information of more complete set of hidden variables. So for that purpose, very similar states are sometimes written in this way. In this situation, not only are the two components correlated in a classical way, when this is plus, when that's minus, but there is also some coherent phase between them. If you measure just one, or if you restrict your attention to one of those, what you get is, in row 1, in this case, is the rank 2. So it's a rank 2 operator. It's either plus or minus, but there is no longer any phase coherence. The act of measurements messes up this entanglement. So in a way, the deviation from this inequality, in fact, the difference between S and its sum, and the sum of its components, that's the entanglement entropy, and it's taken to represent the number of the entanglement. Let me just stop there. So this should alert us that one cannot take things for granted. Still, while the analogy with the classical case in place breaks down, it is of value as a guide. And then in a case, you can start playing this game. You may ask yourself, well, what properties do carry over? And it turns out that entropy subadditivity, the statement that the entropy of the whole is less than sum of the entropies of the subsystems, that is true quantum mechanically as well. The difference between S1, one way to prove this inequality classically is to notice that this condition, the difference of S12 minus S2 can be viewed as the conditional entropy of S1 given N2. In a very concrete sense, it actually equals the average of the entropy of the state 1 conditioned on the state of 2 integrated this entropy of this conditional distribution averaged over the state of the second particle. It works very simply classically. Quantum mechanically, we do not have this tool of conditional representing a state as an integral over conditional distributions. The act of measurement, quantum mechanically, actually affects the state. It's not a passive, there's no passive measurement that we have classically. So this breaks down. But the proof is possible actually by an elementary argument. The argument is actually very simple. Let me just quickly show it here. A state at which there is joint distribution of 1 and 2 can be decorrelated by averaging this matrix over unitary transformations which preserve separately rho 1 and rho 2. Unitary transformations which are product of unitaries, one rotating one subset, the other subset, preserving each one. It's a group of unitaries, and it's just average over the corresponding Haar measure. You find that this state can be presented as an average, probability average of unitary versions of that. And then Jensen inequality permits you to conclude the subadditivity. So it's a different argument, but the bottom line is the same. Also, it's the same inequality. But then, here I guess I spelled the argument which I just read to you. So let me skip over that. The strong subadditivity of quantum entropy is the statement which can be expressed this way. To parse it, for me personally, a better way to read this is to say that the conditional entropy of rho given rho 1, which is this difference between S of rho versus S rho 1, is monotone decreasing in the subsystem size. Classically, it's extremely intuitive because conditional entropy classically answers the question of how much would you learn, how much information would you acquire about the state if you measure it starting from already known what is its subsystem. And then it's rather clear that if you increase the initial information, there is less to be gained. So it's obviously monotone decreasing in rho 1. As I said, quantum mechanically, these concepts do not quite apply. So a way to prove that goes through goes through a proof that the mapping which associate with a state on a composite system rho 1, rho 2, this difference of entropies. So it was a conjecture by Mary Beth Raskai somehow, according to the joint account of the story by Elliot Lieb and Mary Beth Raskai, the way the progress worked was, it was early on suggested that perhaps this mapping is concave, and then the Jensen inequality can be used to prove what you need. Proving concavity of this then was a big challenge, and that's something which took Lieb kind of 2 years to develop. So on this, I should perhaps speed up over this argument. This is the statement that if you have the Lieb-Raskai concavity, then the strong subadditivity would follow. And that's essentially a similar argument to what I described before. It's kind of Jensen inequality related to the fact that you can present the right-hand side as an average of what's on the left, evaluated for a state which is averaged over a group of unitaries. So let me just show how we get to the proof of the Lieb-Raskai concavity. And instead of the argument which was developed by Elliot Lieb, I want to show that this quickly follows from the joint concavity of the parallel sums. And all you need for that, so here is a theorem of Lieb, which is that if you take any sequence of numbers pj whose sum is less or equal than 1, then the mapping from the k tuple a1 up to ak2, this tensor product of fractional powers, is jointly concave. It took some effort to prove that, but here is an elementary proof, again guided by what I said before. You seek a representation of this function in terms of resolvents. Well, here is one. Once you have this representation where this function, it's related to the question which I was asked earlier, representing square root of an operator. It's kind of higher version of that. This operator can be represented as an integral with some positive weights of 1 over 1 sum of the inverses. We saw earlier that these are concave, jointly concave functions, and therefore so is that. End of proof. That's essentially, I think, the last transparency. What I want to say is that, to relate it to entropy. So a streamline proof from the Lieb-Raskai concavity of the mapping which associates to rho 1, 2 entropy. That's the conditional. There's a typo here which I should fix. Essentially, to get into the A log A, you notice that A log A is essentially the derivative of A to power 1 minus epsilon differentiated with respect to epsilon at 0. So the concavity of A to power to fractional power, which we established before, implies that this is concave. When you subtract from a concave function a linear function, the difference is concave. And then elementary argument then permit you to conclude the concavity of the mapping. Okay, I think that one has to read it calmly, and I'm not sure I'm doing a good job reading it. But what I want to say is that the bottom line is that, actually, let me turn to the summary. The bottom line is that these elementary arguments for analysis of convexity can actually be applied to questions which are originally very puzzling in the context of operators theory. So to summarize, there are striking limitations on matrix monotonicity and matrix convexity, where essentially the monotonicity already implies the Herglot's peak property and the spectral representation. And the constructive implication of that is that tests of monotonicity and convexity can be reduced to rather simple differentiation formulas in the simplest setting, and that these techniques actually do apply to cases of interest. That was the main point of this talk. And here are a number of references on the subject. The highlight is work of Loevner, 34, in quick succession, Krauss, 36. And then there is this book by Barry Simon, which he described as a love poem to Loevner, and other works on the mathematical physics of this, going back to Oscar Lanford and Derek Robinson, Lieb Ruskay. Frank Hansen has produced many results on quantum entropy derived from first principles, but usually using tools from differential geometry and Gateau derivatives, etc. And Eric Cullen produces a stream of interesting results in this vein. Whatever I said is a joint work with Giorgio Cipollone. So thank you very much, and thank you for, oh, that's the last transparency. Thank you.
Any questions?
The first theory you described about monotonicity of functions. Is there an implication? Is that function we know is monotone to somehow a way to construct functions that are monotone using this theory you showed it's linear?
Well, for example, the entropy function, or monotone rather than convex, you meant, the two notions go together, because if you have a convex function, I mean, convexity means that, I talked about convexity and switched at some point between convexity and concavity. If you know one, you know the other, because it's just a matter of sign. If you take a convex function, a function is convex if and only if, for every point, the difference between the value of f and that point is monotone. Convexity is monotonicity of the tone. So your question is, are there some functions of interest for which we want to know that they are convex or they are monotone? Is that?
The question is the other way around. As other functions that we know are monotone, we use the theorem to deduce that they're actually linear.
Oh, that they are linear. I do not know such an example, because usually it's much more work to establish that a function is monotone over all linear operators, positive. And Loevner's theorem said that indeed, if you know that much, you can conclude that it's linear, yes. But I do not know a function for which I know a priori convexity without knowing the linearity. Yes?
The beginning of the talk, you showed that some representations of functions which are monotone or concave. I was wondering if this is also true for operators in Hilbert space.
Yes. Actually, all that was said here does extend to, I did not, these formulas actually apply to operators in Hilbert spaces, although you have to, let's see. I feel more comfortable working with operators of compact resolvents, but there's plenty of those examples of those. Take Schrödinger operator and look at its resolvent at zero energy or negative energies. If you take a Schrödinger operator, something which actually is often used in analysis, and Jonathan often has used it. You take essentially if H is P squared plus V and V is positive, then 1 over H plus eta positive, or let me put it this way, H minus E, where E is negative, that's a compact operator in a Hilbert space, which we know actually we are often interested in because it reveals spectral information about the operator. So this is a monotone. The mapping from H to that is convex, has the right convexity property. Or is monotone and convex. Convex or concave, it's 1 over H, you can figure out. And again, linear combinations, often spectral analysis makes heavy use of resolvents, as Jonathan Breuer here knows very well and applies. So that would be the way I would link the two. And there are issues of domains, etc., but this is a bounded operator, and then there is no problem. So, well, thank you.
לא הבנתי.